Hi, I'm Vanati. Today we are going to talk about the FSL tool TrUE-Net, which stands for Triplanar Unit Ensemble Network, which is a deep learning FSL tool for detecting white matter hyperintensities on structural brain MRI. So before getting into the tool, let's have a brief overview of white matter hyperintensities, also known as leukaryosis. So these are lesions in the white matter of the brain which contribute to are the early signs of neurodegeneration, and they are also associated with various cerebrovascular diseases, especially vascular cognitive impairment, and they have age is one of the main risk factors of white matter hyperintensities. They have also been associated with gait related disturbances as well. So here is a sample of white matter hyperintensity, and we have also shown a manual segmentation of hyperintensities along with an automated algorithm results. So how does TrUE-Net work? So what's the generic principle of the TrUE-Net tool? So here we need the training data set, which is used to train the model to identify the features associated with white matter hyperintensities. And then we need a test data set, which is essentially to infer the final results. And the TrUE-Net gives what we call as probability maps, which says how probable each voxel is to have the hyperintensity. And finally, we threshold above a certain level, and we take those as the main hyperintensity regions, as we do with any automated algorithms. Okay, so most of you would be familiar with the earlier tool we have, which is called Bianca, which is also a supervised method for identification of white matter hyperintensities, which is based on k nearest neighbor algorithm. So the TrUE-Net is actually a deep learning based method, and we have various similarities and differences, mainly advantages over Bianca with this advanced tool. So we will first see the similarities. So the first and foremost, both of them were designed for white matter hyperintensities, both deep and periventricular lesions, and both of them are supervised, which would mean that you need to have some manually annotated data for training. So we do have pre-trained models in both cases, we'll come to that. And both of them are multimodal in nature, which means you can actually provide FLAIR and T1 modalities. So there are actually provisions to add more modalities in Bianca, whereas in TrUE-Net you need to train the model fresh whenever you had the new modality. So we do have pre-trained models for FLAIR and T1 separately, and for both FLAIR and T1 in TrUE-Net. But if you need to add any additional modalities, you need to train the model from start. And both of them return the lesion probability map on which you will apply the threshold that you want to obtain the final binary maps of hyperintensities. Now coming to the differences, so TrUE-Net has shown promising results by providing better performance when compared to Bianca, especially in determining the deep lesions which are farther from ventricles. We will see more about it in the actual methodology. And there is a possibility to fine-tune the existing model, which means that you do not have to train the model from scratch when you have a very similar data set. So you can take a pre-trained model and you can actually fine-tune from a few layers from the existing model, and you can just tweak the model a bit to match the characteristics of the new data set. So data preprocessing pipeline is slightly different because you need to add distance maps, which is included in the methodology of TrUE-Net. We will also see that in detail in the upcoming slides. And promising results on different types of lesions. So not only on hyperintensities, even though it's predominantly developed for hyperintensities. So we have obtained some promising results on MS lesions as well, and among other types. But even among hyperintensities, we have obtained promising results in deep lesions. So it's an add-on module to install in FSL. So the installation instructions are also there in the upcoming slides. We'll talk about it a while. And the GPU is needed for best performance. So it's quite a complex algorithm that's used to build TrUE-Net. So as opposed to the normal CPUs that you will use for Bianca. So TrUE-Net requires graphical processing units, For inference, you can actually run it on CPU, even though it might take quite longer, maybe 10 to 15 minutes, depending on your CPU capacity, memory capacity. But then, if you are doing training the model from scratch, you definitely need a GPU card to train your model. So we will see the installation instructions with GPU specific CUDA version as well when we talk about installation. Now coming to methodology, so TrUE-Net is built, it's a deep learning based model. It's built using a very basic architecture of what we call as a U-Net model. So the name U-Net because it resembles alphabet U. So the U-Net falls under an encoder-decoder architecture, right? So that's a basic building block of the triplanar U-Net architecture that we use for the TrUE-Net tool. So how does U-Net work, right? So we have the architecture here. It consists of an encoder and decoder. So when the input is fed into encoder, we actually have a series of what we call as the convolution layers, which using filters. You convolve the filters with the input, and then we also have the downsampling layers, which is indicated by red arrows. With each downsampling, or what we call as pooling, the size of the activation map reduces, which helps us in capturing the localization of the lesion, which actually gets us more and more global information, because in the initial layers the filter encodes the texture of the lesion, right? So the more and more we pool, the filter is now able to see the receptive field of the filter increases, and the filter is able to see more of an image, which helps in getting more contextual information. So at the bottleneck, we actually have more of a location based information than texture based information. Now we have actually lost the texture based information over the pooling layers, right? So that is being recovered in the decoder end of the network, by using what we call as this skip connection layers. So these gray arrows mean that the activation maps from the encoder part is concatenated with the decoder end, which ensures that whatever texture information we have lost over the encoder layers is being appended again to the decoder layers. So, and we also have the location based information which we have preserved. So now at the decoder end, the U-Net combines both the texture information and the location information to give a very accurate segmentation output, or voxel wise classification output, to give the final probability map. Here we show the thresholded version of probability maps, but we do get a very reliable probability map, because especially along the boundaries, because the model is able to encode both the texture and the location based information. Now that we have seen the basic building blocks of TrUE-Net, so what actually happens in the methodology, right? So we have a MRI volume of brain. So here I have shown a flare volume. You can actually give multimodal information, which means there are two channels. You can provide both flare and T1. There is actually provisions to add the number of channels, which means if you want to add only flare, that is also possible, in which case you have to mention the number of input channel as 1 and add flare or T1 as you wish, or you can add both. So let's take an input volume, MRI volume, and we extract 2D slices along all 3 dimensions separately. So first we have axial, and then we have sagittal and coronal slices. And now we apply the 2D U-Net model, which I explained in the last slide, on each of the individual dimensions, and we obtain the output probability map in each dimension. So why do we need in 3 dimensions? So if we do in just 1 dimension, let's say axial, because in most of the cases, most commonly axial has higher resolution. So since we consider the individual slices separately, the U-Net might not be efficient in obtaining the segmentation of contiguous hyperintensity lesions in a more robust manner. So to ensure continuity across slices, we are also taking in the other 3 dimensions so as to have the continuity along the slices, right? So we don't want the lesions to be missed in one of the middle slices, so there is a discontinuity. So that's exactly what we do with this triplanar architecture. It's technically also called as 2.5D architecture because it's not strictly a 3D model. So we apply or we train the models, the 2D models in the individual dimensions, and we obtain the final output in all 3 dimensions, and now we have to combine them to form the final 3D volume. So here we have the slices on the 3 dimensions which we assemble to form the 3D volumes, which are formed from just the individual dimensions. So we have 3D volumes from these 3 dimensions, and we now combine these 3D volumes by taking average of the 3 volumes to get the final probability map. So this is our probability map. This is the output of TrUE-Net, which we have to threshold to get the final binary segmentation map. So one of the main advantage or one of the main novelty of the TrUE-Net is the loss function that we use. So we use a combination of dice loss and cross entropy loss. So to give a brief overview of both, so dice loss is based on the Dice-Sorensen coefficient, so where we have higher metric for heavy amount of overlap. The higher the overlap, the higher the metric. But here we use negative dice loss, which means the higher the overlap, the lower the loss, which is what we want. And the second term is the cross entropy loss, which shows the likelihood, which actually minimizes the negative log likelihood of having the true and the predicted voxel matching, basically, right? So the higher the overlap here also, the lower the loss will be. So here the main idea is, so we have here, you can see the lesions, the white matter lesions, which are closer to the ventricles, and there are a few small lesions which are actually shown by red circles here. So these are very small in size, and they are completely overshadowed by these large lesions, because any segmentation algorithm we train, so they get a lot of instances for training from these periventricular lesions, and hence the algorithms do exceptionally well in determining or identifying these lesions that are closer to ventricles, which are more predominant, and they are very nice to see. Whereas these small lesions in our recent study has shown that they have more association with vascular abnormalities like stroke and other cerebrovascular diseases. So it's equally important to identify these lesions as well, where most of the segmentation algorithms fail. So we wanted to get a high segmentation performance in the deep lesions as well. So we slightly modify our loss functions, especially the cross entropy loss. So I have shown here the a sample image, the same image here, and what we do is we actually take the distance from the ventricles. So as we move farther away from ventricle, the distance increases. So we can use this as a spatial map, but there is still a glitch, right? So if we keep on increasing the distance, we hit the interstitium of the gray and white matter, which the gray matter also has almost the same contrast as the white matter hyperintensities, the deep ones. So we cannot keep on increasing, because then we'll get a lot of false positives in these gray matter boundaries. So we wanted to avoid that, and hence we also take the distance from the gray matter. So now we combine both the distance maps, and we end up with the final distance map, which we call it as D weight, and which is what we use to spatially weight the cross entropy loss. So now we not only calculate the negative log likelihood of what the match between the true and predicted labels, but we also have the weighted loss functions, which means as we move farther away from ventricles, the negative log likelihood, which is to be minimized, increases. So now moving on, we wanted to measure the performance in both deep and periventricular lesions, and as the as the results show here, so we obtained comparable performance for deep and periventricular lesions in 3 datasets. So in a MICAI challenge dataset from the MICAI conference in 2021, so that's a multi-centric data consisting of patients from 3 different centers, and hence the scanner characteristics also vary. So TrUE-Net gave good performance in both deep and periventricular lesions in this dataset, and also we had another neurodegenerative dataset which had subjects with Alzheimer's disease, mild cognitive impairment, including some healthy control, aged subjects where hyperintensities can also normally occur. And we also had Oxford vascular study cohort, including cases with vascular cognitive impairment, and there were also some healthy controls. Okay, so now we move on to how to use TrUE-Net, the most exciting part, right? So we start with the installation of TrUE-Net. So how do you install TrUE-Net? So TrUE-Net, as I mentioned earlier, is an optional component of FSL, and it's available from FSL 607.13 or the newer versions. So you, as usual, you install using Python FSL installer. The detailed instructions are provided in the FSL page, so please visit there for more instructions. I'm just going to give you an overview of installation here. So you use the Python FSL installer, and you actually add an extra flag, and you just mention TrUE-Net, so that would install TrUE-Net as an additional component module to FSL. So if you have already installed FSL, and if you just want to update the installation, so you can of course do that too. So you can do update FSL release, and you can say again extra TrUE-Net using the extra flag. So now if you need, so usually for installing deep learning based pipelines, especially installing TrUE-Net does install some deep learning software libraries. So if you need to have a specific CUDA version which will actually be compatible with your GPU or with your CUDNN version, so that's quite common. So you can actually do so with the additional CUDA flag as well. So here we have shown for CUDA version, specific version of 11.2. So feel free to change the version number, and you can install the TrUE-Net for very specific version. So now we talk about the data pre-processing or the preparation of data. So the input modalities, so we have FLAIR or T1 volumes or both. So we have. So the first thing we do is we actually align the input volumes, the 3D volumes, to the standard MNI template by aligning the geometry closer to the MNI template. And we also do FSL brain extraction using BED tool, where we do skull stripping, and then we do FSL fast to correct the bias field inhomogeneities, and finally we have the data ready to apply the TrUE-Net. So here the additional pre-processing step we do is to get the distance maps, right? So essentially we start, this is the command we use, it's prepare TrUE-Net data, right? So we have the FLAIR volume. So here if you have FLAIR volume, you can give the FLAIR name, the T1 volume, the T1 image base name, and then you actually need to provide the out name, which is the output base names, right? So if you, for example, if you want to save everything as subject 1, so you basically just provide subject 1 as the name. So FLAIR T1 will be appended to it. And then the manual mask. So there is no pre-processing done on manual mask per se, but the manual mask name, the name of the file is renamed to as per the file conventions required to run the TrUE-Net model. So here I think it's worthwhile to add that you can actually do your own pre-processing pipeline, but then the name of the files should be compatible with what the TrUE-Net tool expects, which we will actually see in the upcoming slides. So if you run the prepare TrUE-Net data, this automatically performs the naming convention. So you don't have to do anything in addition. In case if you do the pre-processing on your own, please notice the naming convention and please stick to it. And we do have an option called no dist maps. So as we saw in the loss function slide, so we actually use the distance maps to basically use a better loss function to scale the loss functions. But then if you are actually using the model, essentially if you are only going to use TrUE-Net for inference, or if you are planning to train without the weighing function, the spatial weighting, so you can actually skip the distance maps because it takes quite a while. So you can use this no dist map flags. So if this flag is given, the distance maps will not be calculated. So there are some use cases where that can be quite useful, right? So the first one is where you actually use distance map for hyperintensities because the deep lesions occur farther away. And there are some use cases like we also use TrUE-Net for brain lesion segmentation, for instance brain tumor segmentation. So there is no spatial prior, like there is no study to support that the brain tumors occur in certain region of brain, so they can actually happen anywhere. So in those cases the distance map really doesn't make sense. So if you are using for any other application, so please feel free to activate this no distance map, add this flag, so the distance map will not be estimated. And finally, we do have keep intermediate flag, where you get to keep the intermediate results, for example skull stripping without bias field correction. So all those results are also accessible, so if you activate the flag. And we also have the verbose flag. Okay, so this is the naming convention I was talking about. So I have shown for two different samples. So we do have two different subjects, and this is the base name that's given. For example, if GE3T underscore 103 is the subject base name, the out name. And so once the pre-processing is done, so these are the file names that are being appended to it. So the input flare is basically the base name underscore flare, and the distance from the gray matter, if you remember, we had two distance maps and we added to get the final distance map. So the distance from gray matter is base name underscore gm dist, and then the distance from the ventricle is basically the base name underscore vent dist. Okay, and then we have base name underscore t1, that's the t1 input modality, and finally we have base name underscore manual mask. So if you don't want to provide manual mask, but you can actually name as per the convention on your own, so you are welcome to do that as well. So the same has been shown for another subject, so you get a better idea of how to name. But this is the naming convention. These are the file names that the TrUE-Net tool would expect to see in the input directory. Okay, so that's the base name, and these are the pre-processed data files. Right. So now the subcommands in TrUE-Net. So these are the subcommands currently available. We will go through this one by one. The first one is train module, where you train the models from scratch. And the second one is evaluate. If you have a pre-trained model or if you have trained a model recently, so you can just apply the model and get the segmentation performance on a specific data set. And then we have a fine-tune subroutine, which actually tweaks the model slightly when you apply on a new data set. And then we have cross-validate, which is essentially cross-validation of TrUE-Net model on a data set to know the generalization capability of TrUE-Net. For example, if you want to do a fold validation, you can do with the cross-validate subcommand. So with the 5-fold validation, you will actually keep aside 5 folds of test data. So we will see that in detail later, but this tells you how generalizable or what's the upper and lower limit on the capabilities of TrUE-Net on a given data set if you want to analyze it thoroughly. Okay, so we start with TrUE-Net evaluate because that's the easiest option available. So when you have a pre-trained model available, so we also have made some pre-trained models which are trained on UK Biobank, and the MICAI challenge dataset available for evaluation. So the first thing you want to do when you have a dataset is you want to apply the pre-trained model using TrUE-Net evaluate subcommand, and you want to see how well the model performs before you want to proceed to the training or fine-tuning option. You want to see what's the capability of TrUE-Net first. Okay, so let's get to the tool. So TrUE-Net, and we have the subcommand evaluate, and the first option, there are three mandatory options. The first one is the input directory. So this is the directory name of the directory where your files are available. Okay, and the second is the name of the model. If you are using a pre-trained models that is available with TrUE-Net, so you can just use the keyword, which is essentially here in the example it's given MWSC, which stands for the MICAI challenge dataset trained model, using both FLAIR and T1. And then the output directory, which gives the name of the output directory. So here dataset results1 is the folder in which we are going to save. So I suggest making this folder beforehand, because this doesn't create the folder, right? If you don't have the folder already, it will throw an error saying that the folder doesn't exist. So please create the folder before you run the command. So here we have TrUE-Net evaluate I, which is basically the input directory. So the input files can be found here. And then we have given the model using this keyword, which shows that we are using a pre-trained model, MICAI challenge trained model, and then the output directory name is provided here. So just a sample example, right? So how the input directory is given. So for example, I have given -i dataset A input. So that's a folder name, and the data is available here. So you can have multiple subjects, so you can dump multiple subjects for files in the same folder and call the folder, in which case it will actually sequentially run through all the files in this particular folder, right? So for example, there are two subjects present in the same directory, so it will actually take this particular all the subjects that are in this particular directory. It's very handy for training, especially because in evaluate you can also have individual subject folders as well, like what we see here, right? So here dataset A and the subject name, you can see only the files related to that particular subject is available here, right? So you can give either way. When you give for training, it is recommended to put all the subjects just in one folder, so it actually takes all the subjects for training and loops through it. So there are optional arguments available for TrUE-Net evaluate. The first one is essential. I'm just going to go through a few of them. The first one is use CPU. So this is essentially if your TrUE-Net is running on a machine where you have GPU, it will automatically switch to GPU. That's the priority that's given. If there is no GPU in your machine, in the absence of GPU card, it will run on CPU. This flag is used if you have a GPU card on your system, or a server, but if you still want to use CPU for whatever reasons, right? So if your GPU card is busy, or if you are on the queue in shared resources, if you want to deliberately use CPU and finish the job earlier, you can use the use GPU flag, and this will switch to CPU and it will just run slightly slower, but it will run on CPU. I wouldn't recommend use CPU option for training, because you will be training forever. But if you are actually using only for evaluate, it's okay to use CPU. It's slightly slower, but it's okay. So and the next option is N class. So you are supposed to provide the number of classes which is used for training the model. So if you have a pre-trained model, make sure to provide the number of classes which is used to train the model. So now for all the pre-trained models, we use only two classes, which is either it's a hyper intensity or not. It's a binary classification. So for here we use N class as 2. If you are, as I said, TrUE-Net is a very versatile tool we have used for multiple applications. In case if you want to train for any other brain lesion or many types of brain lesions, you can have corresponding manual segmentation, and you can change the number of classes. For example, if there are 4 types of lesions, please feel free to add 4 and keep training. And you can do the same for evaluate as well. So intermediate, essentially to save intermediate predictions, so we have individual planes. So if you want to save axial, sagittal and coronal, you can do that. The final result is actually also saved anyways. And V is a verbose flag, which we saw earlier. So it actually lists individual steps as and when you run if you switch this flag on. So I have only gone through few of the important arguments or options available. So there are actually more options available. So please visit the full documentation, the documentation link to know more about the additional options available for all the subroutines. I am going to only go through the more basic and important options. Now we talk a bit more about pre-trained models. So as I told you earlier, there is this the flag M, and then we use the keyword. That keyword is going to tell you which model we are planning to use. And here is essentially the option name that we are using for the different models. So let's just go through the models. So there are 2 datasets which we used for training. One is MICAI challenge dataset and another one is a small subsample of UK Biobank dataset consisting of less than 20 subjects. It's not trained on a large dataset, but this data is taken from UK Biobank. And here the modalities that we use. So for each of the dataset we used either T1, either flare or both flare and T1, right? So if we use both flare and T1, we use just the dataset name without any post keyword. If we use flare, we use the dataset name underscore flare, which means the model was trained only on flare. And then for T1, we use the dataset name underscore T1. The same goes for UK Biobank as well, both T1 and flare. So we use only the dataset name, and then for flare we have the flare appended to it, and then T1 we have T1 keyword appended to it. So here, which shows that we take a MICAI challenge trained dataset, trained model, which was trained on both flare and T1 modalities. So regarding what model I would recommend while training, it's completely dependent on the dataset details. So one thing to note here is that the MICAI challenge dataset consists of 60 subjects, which was used for training. So the model is trained on 60, whereas for UK Biobank the model is trained on less than 20 subjects using an omni-supervised framework, which was guided using age prediction task. I don't want to go into much detail, but it is actually trained in a more sophisticated manner to overcome the shortage of training data that we used. So I would recommend MICAI challenge dataset because it was trained on slightly large dataset, but then UK Biobank dataset has also shown good results. Okay, so the results. So I have shown here the main result and also the intermediate ones. So the axial, coronal and sagittal results are shown with the corresponding post appendages. So you can actually see axial here, which is the axial output, coronal 3D volume and sagittal, and finally the combined output, the final output is given here, which is essentially without any post appendage. It just shows that this output was detected using just T1 as modality, the input modality, using some model which was pre-trained only using T1, which actually, if there are no modality name specified, which means it's trained using both. Okay, so now here is the command we use for thresholding the probability map, because if this is the input given, so the TrUE-Net provides a probability map output, so that looks like that, and then we have to threshold to get the final binary map. So here we use FSL maths command, so that's the output probability map that we obtained, and we use the threshold of 0.5 and then binarize it. Anything above 0.5 is binarized to a binary segmentation map, which is essentially you can provide an output name. So that's the final map we get. So now to get the segmentation performance or overlap measures like the dice and sensitivity, specificity, voxel level, false positive rates. So there are a lot of segmentation metrics available to calculate once you have the binary segmentation map, so that you can use any tool to do that, including our earlier tool which is called Bianca overlap measures, which is part of Bianca. So please check that out, and you can use the same tool on the final binary segmentation map to get the measures here too. The link is provided here, so the same tool can be used. Next we get to the train option. So here example is provided, right? The first mandatory argument we need, or the option we need, is the input again. So I gave an overview of how you can actually provide the input directory name, and all the files in the directory will be taken. All the subject files will be taken. And then we have the label directory, because we need manual annotation for training from scratch. So we need to have a label directory where the manual annotation labels are provided. If you have the input images and the label directory in the same folder, please feel free to repeat it again. And then we have the model directory. So this is the directory in which the trained model will be saved. And then here you have an option of training the model with weighted or without weighted. So the weighted, you will use the spatial distribution, the distance map, right? So the GM distance and vent distance map, which we saw in the earlier slides, so in the loss function. So if you give loss weighted, this would need the distance maps. So if you give the loss n weighted, so you have it here somewhere. Yeah, so loss function, it can have two values, which is weighted or n weighted. If you have n weighted, which means no weighting is required, it will be trained in a normal manner. You don't need distance maps. Okay, and these are the advanced options available. So the first one is the training proportion, right? So most of these options have default values which have been optimized to give a good performance. So they have been already shown to provide optimal performance. So if you want to run without touching any of these options, that's perfectly fine. If you are doing some analysis and if you are familiar with the technical aspects of TrUE-Net, so you can tweak these advanced options as well, right? So the first option is the training proportion, right, which shows out of total number of subjects you have, what is the proportion of subjects you would use for training. And the second is batch factor, and then you have loss function, what type of loss function, the distance maps, right, the directory in which the gray matter distance map and the ventricle distance maps are saved. And then so you have number of classes, which I explained already, the plane, right? So if you want to, you can actually individually train for axial alone, sagittal alone, and coronal alone. If you give all, which is the default value, then the TrUE-Net is train on all three dimensions, and that is essentially what we would recommend. If there is shortage of time or if you are resource constrained, you can run on any of the acquisition plane, and we would recommend whichever plane has higher resolution, right? Most commonly it's axial, but you have to check the 3D volumes before you do the training. Data augmentation, so what is the factor you want to augment with, and save and resume training. Okay, so we want to keep this flag always, it would be good to have it true. The default option is false, because whenever you switch it on, it's going to save the whole model, which will take some memory. Okay, the advantage with this is that if your task or the job is interrupted in the middle due to power outages or quota exceeding options and all those things, so you can actually save the model will be saved, and when you resume your job again, it will not train from beginning, but it would rather train from where it stopped. So it is essentially good in a shared resource environment where your job is constrained by some queue or some running time and all those things. So in those cases, if memory is not an issue, it would take somewhere around anywhere between 30 to 100 GB depending on MB, depending on the model size and the data that you use. So I would recommend switching it on if you are running it on a shared resource. And then initial learning rate, right? So you will use a learning rate to train a model, and the learning rate will be subsequently reduced using a scheduler, but this is essentially what you would specify as an initial learning rate for training the model. The default option is 10 power minus 3, so you can change it slightly, but you have to handle this with caution. You cannot go too low or too high. Yeah, so we have shown a sample distance maps here, and this is what I had explained before also. So that is important for the loss function. So that is one of the important advanced options you might want to consider. So these are optimizer parameters. I really think it is good not to touch this if you are not very well versed in the technical aspects of it. So this actually tells you what optimizer to use and what's the optimizer parameters, and what's the number of epochs you might want to train, and then what is the best way to save the model. So the default option we do is essentially the last model that's saved. If you want to save the best model, you can always change it to best, right, when you use early stopping. So the default patient value is 20, which means it will wait for 20 epochs before you actually stop training. Otherwise you can keep on going. So if you are not familiar with these options, completely disregard what I'm saying, leave it to default, and please run the model. It should be fine. Right, so some of the segmentation results. So this is how the results look like, right? So we actually here the yellow voxels indicate the true positive voxels, and then the red voxels indicate the false positives, and the blue voxels indicate the false negatives. As you can see, it's essentially providing excellent segmentation, and so the input images are shown and the segmentation output is shown here. So even in the variation with the lesion load, and also in the contrast and intensity characteristics, the TrUE-Net is able to perform well, and it has provided better segmentation than Bianca as well. So for more details you can always read the paper, but what I wanted to mention here is that we have obtained very good results for the deep lesions as well, the lesions that are farther away from ventricles, which has been quite a challenge for various automated algorithms. So some of the I want to include some of the advanced applications of TrUE-Net here. So we also applied the TrUE-Net model for brain tumor segmentation. So here that's the ground truth and prediction. You can see that it actually provided a good prediction for brain tumor segmentation as well. So again, for more details you can refer to the paper, but there are additional applications that you can train the TrUE-Net for. It's a very versatile tool, and all you need is basically the right number of classes to be inputted, and then the appropriate manual segmentation maps. And again an output showing multiple sclerosis segmentation. So here that's a manual mask, and this is the paper that applied TrUE-Net and compared it with U-Net, and you can see that's a lot of false negatives which is shown in blue, whereas TrUE-Net is giving quite a good segmentation with a bit of false positives. But yeah, so it's not missing out any lesions in fact. Okay, so if you remember, I also introduced two additional subcommands for TrUE-Net. So one is fine tuning and the other one is the cross validate options. So we are going to go through it now. So if you remember the U-Net building block that I explained earlier, so we actually have the layer wise architecture of U-Net. So what we do in fine tuning is that we actually tweak the model little bit to adjust to the lesion characteristics of the new data set, which means we don't want to train the whole model. We only want to fine tune some layers of the U-Net, keeping the other layers frozen, right? So if I say that I'm going to fine tune layer 1, which means all the layers in the U-Net will other than layer 1 will be frozen, which means the weights will not be updated, and during back propagation the gradient estimation and updation will not happen, right? So only the layers that are specified will be updated. So now we number the layers starting from the decoder end, which is the output layer. So output layer is layer 1, and then the output layer without the final filter is layer 2, and then we keep increasing the layer number as indicated here. The bottleneck is layer 5, and then we go backwards, right? So all you have to do in fine tuning is that you provide the layer number or numbers of layers. So usually we start our fine tuning from the output layer onwards. So we keep on changing or updating the weights for the output layer, and the initial few layers are usually kept frozen because, as I told you earlier, they capture only the texture information, right? They don't capture high level details, which is essential and which is the main component that changes across different data sets. So you always start the fine tuning from the outermost layers. And the another thing I wanted to mention here is that this is not a retraining. This is called fine tuning because we want to do only a fine tweaking, right? Which means that the learning rate that we use for fine tuning is much lower than the learning rate we use for training. If you remember, I mentioned an option called ILR, the initial learning rate, in the previous slide. So here you actually specify lower learning rates. You don't use higher learning rates. Right, so what are the options? So the options, the subcommand is called fine tuning, right? So there are a lot of options again. So the advanced options, I'm not going to go in detail, right? So again, so here um, I have created a new directory, model fine tuned, and there is a um, sample call here, which is essentially fine tune. I is again the input directory where the data is available, right? So for fine tuning you need the new data, and again you need the new manual labels as well, right? So that is provided here, and you also need a pre-trained model. You already need a you need an already trained model which you will actually fine tune, tweak to get the new model. So here I have actually taken the pre-trained model, the Mikai challenge trained data, the data trained model with both FLAIR and T1, and then the output directory where the fine-tuned model will be saved, and then this is essentially the label directory where the manually labeled annotations are available, and then here also I am training with, or I am fine-tuning with, the weighted loss function only. So one optional argument which you need to be mindful of for here is essentially the fine-tuning layers, which is called FT layer flag. You can use this option, and then you can specify the layer number. So here I'm using default 1 and 2, which means the last couple of layers are being fine-tuned. If you want to increase more, if you want to essentially fine tune more layers, you just keep adding on more layer numbers, right? And then the final option is TrUE-Net cross validate, right? So here usually we do n-fold cross validations, or leave one out all validation is also possible, right? So we do these validation to determine the generalization capability of any machine learning model, any automated algorithm. If we want to find it, what is the maximum and minimum limit of its capability, we do the fold validations, right? The higher the fold, the lower capability of the upper limit of model capability you will get, and the higher the number of folds, you will get the lowest capability of the model, right? So now the most popular cross validation is people do 5-fold cross validation. So we have TrUE-Net cross validate, and the same options hold. For example, the mandatory options are input directory, label directory, and output directory, and we additionally have these arguments, which is the number of folds you want. As I said, if you don't change it, the default number is 5, where you actually split the data into 5 folds, and you essentially keep each fold aside for testing and train, so that you can actually evaluate the performance of the model in a more generalizable manner, in more cross-validated manner, and you can actually get the average performance. This shows how good your model is performing on different buckets of data. Right, and we also have an option called resume fold, which means again this is very similar to save and resume option you have, whereas in a very resource constrained environment, if you want to save and resume from where you left, so you can do so. Here if you can actually save the fold if you have already performed 3 folds and if your job has ended in queue. If you run this with the save resume fold option, the default option is 1, which means it's basically you can resume. If that option is switched to 1, which means that when you resume training, it will not run the first 3 folds, it will only run the last 2 folds. Okay, so this also saves time and resources. Okay, so let's go through the quick summary of the things that are discussed here. So the first one is that the deep learning, we are introducing a deep learning tool, FSL TrUE-Net, for lesion segmentation. It uses the triplanar architecture and uses U-Net as a building block, and hence the name triplanar U-Net ensemble network. It has various subroutines to enable various functions, including training the model from scratch or evaluating an already pre-trained model or fine-tune a model to tweak the model to match the characteristics of or adapt to the new dataset. And finally we have cross-validate option, which does directly cross-validation without you have to do the training and evaluate alternatively. So you can do so with the train and evaluate functions, but we have done it implicitly in cross-validate. All you have to mention is the number of folds. If you have leave one out, you can just give the number of folds equal to the number of subjects in the data. That will actually do leave one out validation. And then it requires you to provide input and output directories. And then the most important thing to note again is essentially the naming conventions. Please be mindful of naming conventions, and the files need to be named in a specific format to be recognized by the TrUE-Net module. And as I have shown some example applications and also results, so we have actually seen promising results in various applications, including tumor segmentation and MS lesion segmentation, apart from the actual hyperintensity segmentation. And we did actually get some preliminary results on brain histological data as well. So I have not included them here, but so they are actually quite it's a very versatile tool. You can train for different applications. And we have more information available on the FSL documentation page. So the link is provided here. Please feel free to go and check out for more advanced options and also some of the recommendations and suggestions we have regarding using this tool, right? So with this, I would like to conclude my talk on TrUE-Net. I hope you all enjoyed it, and I wish you good luck in trying out our new tool. And please feel free to contact us regarding any suggestions you have regarding the tool or any clarifications you would need. And thank you very much for your attention.